Hello and welcome to podcast.init, the podcast about Python and the people who make it great. When you're ready to launch your next app or want to try a project you hear about on the show, you'll need somewhere to deploy it, so take a look at our friends over at Linode. With the launch of their managed Kubernetes platform, it's easy to get started with the next generation of deployment and scaling, powered by the battle-tested Linode platform, including simple pricing, node balancers, 40 gigabit networking, dedicated CPU and GPU instances, and worldwide data centers. Go to pythonpodcast.com/linode, that's Linode, today and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. So now your modern data stack is set up. How is everyone going to find the data they need and understand it? Select Star is a data discovery platform that automatically analyzes and documents your data. For every table in Select Star, you can find out where the data originated, which dashboards are built on top of it, who's using it in the company, and how they're using it, all the way down to the SQL queries. Best of all, it's simple to set up, and easy for both engineering and operations teams to use. With Select Star's data catalog, a single source of truth for your data is built in minutes, even across thousands of datasets. Try it out for free and double the length of your free trial today at pythonpodcast.com/selectstar. You'll also get a swag package when you continue on a paid plan. Your host as usual is Tobias Macy, and today I'm interviewing Ryan Abernathy and Joe Hamman about Pangeo, a community platform for big data geoscience. So Ryan, can you start by introducing yourself?
So I am a Python hacker who moonlights as a professor of oceanography at Columbia University. I have been involved in both science and software for about 10 years now, and it's always, evolving where I'm focused. But right now, I'm very focused and very engaged on this Pangeo project, and so we're really excited to share what we've been doing with you.
And Joe, how about yourself?
Yeah, so my name is Joe Hamman. I'm a climate scientist and an engineer. My day job is the technology director at the nonprofit Carbon Plan. And there we do data science and policy around the climate problem. My path to this podcast, I guess, is largely through my scientific research. And I ended up working on the XArray project, which we'll get into later, but turned into the Pangeo project anyways. So I started doing that also about 10 years ago. Have really enjoyed my time in the Python world.
Yeah, definitely interested to dig more into the history of XArray and Pangeo and how they relate. But before we do that, Ryan, why don't you share how you first got introduced to Python?
I went to grad school at MIT. In my work, I work with a lot of data from satellites and simulations of the ocean. So I'm an oceanographer. I started grad school in 2006, and I was given MATLAB. That's what everyone was doing. Background prior to that as a programmer, I knew how to code in PHP, I knew a little Ruby, I knew Java, and MATLAB was new to me. I liked some things about it, but after doing my first project, I was kind of just like, I need to do an open source something. And that was about 2008. And at that time, scientific Python was just starting to emerge. I was early enough that I compiled and built NumPy, SciPy, Matplotlib from source, before there was all these great installers like we have today. It just took off. I loved using it. I wrote all my stuff in it, and I did a bunch of research with it. But then the real turning point was when I started to get involved in community open source, which happened more around probably 2014, 2015.
And Joe, do you remember how you first got introduced to Python?
Yeah, my story is not all that different from Ryan's. I was in graduate school at the University of Washington, and the lab I was in had historically used a really wide range of programming tools, including C and Fortran and Perl, and kind of all wired together in a web of shell scripts. And this is how the world worked there. And so my advisor at the time was interested in focusing the group on Python and needed a test subject or a guinea pig. And he said, hey, why don't you go learn how to do this and see how it works? And he was also learning at the time. So that's how I got started. What really got me excited and curious was the community aspect of Python. And I was just like, this is so cool. There's, groups of people. They don't necessarily work in the same place, but they're working on the same tool because it meets their needs and it scratches an itch in one way or another. And that sort of community focus of the Python world is really what drew me in. And I went from teaching myself to contributing to some packages just out of kind of curiosity and interest in how that all worked.
And so that has led you both to the Pangeo project, which brings us here today. I'm wondering if you can give a bit of an overview about what that project is, some of its scope, and maybe the story behind it and how you each got involved with it.
It all started with XArray, right? So we need to talk a little bit about XArray. So XArray is a fantastic tool for data science, particularly for scientific data, which doesn't necessarily fit into that tabular data model that Pandas addresses so well. Back in around 2013 to 2014, a lot of us who were working with scientific data in Earth system science, so like big satellite data sets or model simulations, we all had our own little private version of something that looked like XArray. It was basically some kind of data structure that held together many different NumPy arrays that were related to each other, maybe some metadata thrown in there. And we were writing sort of these custom wrappers, custom, layers to do things with these data structures. Turns out someone who's a much better programmer than me, and definitely than I was at that time, started developing something like that and did a really, really great job. And that was Stefan Hoyer. And so, basically when I discovered XArray, I immediately stopped working on my own little thing that did this job and started using XArray and then contributing to XArray. And on the XArray mailing list, there was kind of a lot of traffic between people in our research field, Earth system science, let's just call it. And we really had the idea that we should coordinate our efforts and really try and get some momentum going, because XArray was useful, but at the same time, there was a lot more unrealized potential, particularly in scaling out XArray to do really big, large-scale data processing. And around that time, some data sets were coming out that we were measuring in petabytes. So in particular, I remember this one simulation that was run by some colleagues at NASA JPL. It was an ocean model simulation, this gorgeous, super high resolution, high fidelity simulation of the global ocean. So we're talking about simulating the global ocean at 1 kilometer mesh resolution. And it dumped out over a petabyte of data onto like one of these supercomputers at NASA. And I remember feeling so frustrated that like it was pretty easy for that model to run. It wasn't trivial, but like it was straightforward. Like those HPC simulation codes are designed to scale out to tens or hundreds of thousands of CPU cores. But we really had no analysis tools that could then deal with the data from that simulation and actually do science with it. And there were a lot of other people in the same boat at that time. And so we wanted to find a solution to this sort of, scaling data analytics problem. We basically organized a workshop and got people together in person, back when we used to get together in person. And that's how Pangeo was born. And maybe Joe can tell the story of what happened at that meeting.
We'll say 20 folks at this meeting at Columbia that Brian hosted and a bunch of us came out for. And we kind of laid out what are the key challenges facing the geoscience community when it comes to software and data and looking forward. What is the world we want to see exist? And, out of that grew the mission of Pangeo and some ideas for projects that we could work on. At the core of that was really connecting XArray and Dask to enable kind of parallel scalable data analysis that was built on top of XArray and making that interactive. And so we also had a focus on bringing in interactive computing using the Jupyter project. After the workshop, we had some findings. There was a website that I think probably still exists with a couple ideas on it. Shortly thereafter, a proposal call came out from the National Science Foundation. We responded to that proposal call and got the project funded. Ryan and I were both on that. Ryan was the lead PI. So for 3 years, we used that funding to integrate XArray and Dask and Jupyter into what was really the beginnings of the Pangeo project, these kind of connections that enabled interactive, scalable data analysis on the types of data that a lot of geoscientists are using.
Yeah, and when I was starting to prepare for this podcast and digging into some of the documentation and the resources around it, as I was hearing about it from other folks that led me in this direction, it's not so much that it's a single project that you can pip install as you would with XArray or Dask, as it is that it's sort of this parent community that works to bring together these projects, as you said. And so there's no single sort of Pangeo project per se from a software perspective as it is a project to enable these types of research that you're discussing. I'm curious if you can maybe talk to some of the interesting challenges and perspective that helps bring at a sort of software and community level to say, we have the Pangeo project, but there's no actual Pangeo source code that you can deal with, and just how you manage that messaging and help using the Pangeo project as this kind of umbrella to bring all these people together.
It's a great question, and it goes to the heart of what Pangeo is. I think what we have done is bundle together a lot of different tools that in isolation may not seem as relevant to the geoscience community. By bundling them together and working to make them integrate, we have presented them as a unified solution. And I think that was really necessary because at this stage, a lot of the community was thinking about transitioning from much more monolithic analysis environments like IDL or MATLAB. And a lot of scientists, when they would look at Python, they would kind of throw up their hands and say, there's a million different packages, what am I supposed to use, And there is this sort of core consensus for scientific Python, well, NumPy and Matplotlib. They basically get you to MATLAB-like parity. But there's actually a lot more higher level capabilities that libraries like XArray and Pandas give you. What bundling stuff together achieved was a couple different things. One, it made it possible to fund from the National Science Foundation. The federal government spends a ton of money on software development activities, but a lot of it is really wasted on projects that don't have a lot of users or don't have a lot of impacts. And at the same time, we know that the open source world, it's chronically underfunded proportionate to its impact. We were able to, by bundling stuff together, we were able to essentially market these tools as one unified solution that a funding agency could get behind and say, oh yeah, we see how this aligns with our mission and the things we want to support. And so they've been able to fund it. And at the same time, by bundling them together, we've also made it, I think, more accessible to institutions to adopt this software stack. One good example of that is the National Center for Atmospheric Research, a really major, large research lab in climate and atmospheric science. Pangeo is their in-house analysis stack, sort of transitioning away from an older tool that they used to maintain a domain-specific analysis language called NCL, NCAR Command Language. And I don't see that could have happened if we didn't try to create this narrative of how all these tools work together to solve real end-to-end workflows. But the downside of this is I think there's still a lot of confusion about what Pangeo is. Is it a group of people? Is it a software? Is it a cloud infrastructure? The real answer is kind of all of the above.
If I can zoom in on one thing, I think that might be another interesting way to look at what the Pangeo project has done and how to think about it. The life cycle of a scientific researcher's idea is usually to start doing some data analysis, run into a bunch of problems, software doesn't solve all problems, and so you have to write some code yourself. And scientists have for a long time been really good at kind of hacking their way to the finish line. And what we did in Pangeo is kind of break that pattern and insert some community opportunities for getting help, collaborating with developers on all of the various touch points of the software ecosystem that scientists were using. And rather than say, okay, I'm going to hack my way to the finish line and say, hey, okay, now we start integrating and working with the developers of these packages that might be able to help us fulfill our goal without going through laborious hacky process. So what that's done is use case driven development of a bunch of these individual software libraries. And overall, kind of it's the rising tide lifts all boats idea. A bunch of those use cases then get solved for the whole community. I think the community has caught on to this that, okay, I could hack my way around this, or I could open an issue on GitHub. That might motivate some conversation. Maybe maybe someone else knows how to fix that. And eventually that ends up in a library like XArray or Dask or something. Then that's a solved problem for a lot of people. So that kind of broke the normal development cycle, and it's been a flywheel effect that has extended beyond just the core climate science use cases. One of the coolest parts about what Pangeo has accomplished is rethink how that development cycle works.
You mentioned that the core elements of the stack are XArray, Dask, and Jupyter, and being able to tie them all together to be able to do this multidimensional analysis in a scale-out format with an appealing user interface. And given that core structure that people can build off of, I'm curious what types of extensions and kind of peripheral projects have been built around that core that may not necessarily be considered part of the broader Pangeo umbrella, but are part of that same community.
There's an image a lot of us have in our head of the Python ecosystem as kind of an onion where Python is in the middle and you have some foundational libraries, say NumPy and Jupyter. And then a layer further out on the onion might be XArray and Pandas and a few of these higher level data analysis tools. What we've found is that better integrating all of those foundational tools, we enabled the development of a bunch of domain-specific tools. And so I think one of the coolest things that we've seen in the last few years is that now you have a package for each domain kind of developing that is built on top of this kind of deep stack of well-connected tools. And so that's things like a LiDAR processing library for looking at data coming out of a NASA satellite, or a library for doing high dimensional grid analysis and that sort of thing. So the way that the ecosystem has kind of blossomed around that is, I think, a function of the fact that these foundational tools solve the core problem. And then there's just like the last mile problem that individuals have been able to tackle on their own.
We've been trying to advance this sort of architecture for what a package in our ecosystem would do. We had this on our website, a couple of like principles that we would encourage those packages to follow. But the basic idea is like, if we have tools that can sort of consume and produce XArray datasets lazily, we get a lot of interoperability out of that. Traditionally, a lot of geoscience workflows have interoperated through files. So like you'll have a command line tool that like reads a file and then like writes a file. And these are usually netcdf files, which is like this really metadata rich like format for exchanging information. And what we're trying to do with Pangeo is to not touch the file system, but have packages that can pass information to each other at this high level, maybe, annotating their results with, units or extra metadata or, things like that, and then be able to chain different pieces of this ecosystem together. So like one specific example of a package that we just came out with that I feel like it really exemplifies this is this tool called GCM filters. It is a tool for doing convolution-based filtering of data that lives on these complex meshes that we use in Earth system modeling, right? So a very common like data analysis need is to like do smoothing-based convolution. And like SciPy or like scikit image or something, they all do this sort of stuff, but only in sort of rectangular image-based space. What we have instead in the geosciences is like we have to do convolution on this sphere in like a curvilinear coordinate system with like this irregular mesh. And so by leveraging the Pangeo ecosystem, we could write code that really just targeted that key piece. Doesn't have to worry about like I/O. It doesn't have to worry about like how to parallelize those operations. We just consume and produce XArray data sets, and then it can integrate with the rest of the ecosystem. And that's what we're going for, but it's kind of hard. It's a long road and doesn't always work out. It's not always so clean and neat. And there's still plenty of confusion and duplication and inefficiencies in this ecosystem. I don't want to suggest that it's like solved. It's more of a vision of how we'd like things to work.
In terms of the scientific domains that you see orienting around the Pangeo project and the Pangeo stack, I'm wondering if you can maybe categorize them a bit and talk to some of the sources of pain that they're experiencing in their maybe so-called native ecosystems that pushes them in the direction of investigating and adopting Pangeo to help solve their problems, and maybe some of the ways that Pangeo can act as a force multiplier by being this sort of common infrastructure that different domains can collaborate with.
Climate science was the core one. And that's what the sort of a lot of the early motivation for use cases and applications and those pain points came out of climate science. And so there we were working with very large, so petabyte scale collections of multidimensional data. There were access problems to that data. It was mostly sitting behind FTP servers or HTTP servers. Individuals or individual research groups would grab some part of it. They would do their research on it. Climate science, we came in and said, okay, so let's start by making it easier to work with that data using XArray and Dask. And since then, we haven't gotten into it yet, but cloud computing has become a larger and larger part of what the Pangeo project has spent its time focused on. And that's largely because it brings to the forefront this opportunity for a data commons-like environment where data is accessible to multiple researchers or research groups. And in the climate sciences, we're starting to see that by putting a bunch of climate data. So Ryan has led a project to put over a petabyte of data from the coupled model intercomparison project into the public cloud. And that's available to all researchers anywhere around the world now in both Amazon or Google Cloud. And that's really kind of changing the game for how researchers access this data. Before, you either had to work at a place that could store that much data, which aren't very many places in the world, or you had to choose a small subset to work on. So today, that's a totally different way of operating on the data.
In terms of the domains, I guess, who is using it and how they end up using it, I think the core nucleus has always been like with the stuff that Joe and I and people in our sort of narrow radius do. It's like analysis of high resolution Earth system observations and simulations. Really focus on this data analysis problem, right? Because like I said earlier, like there's kind of paradox that right now in Earth system science, our ability to simulate has actually outpaced our ability to understand those simulations because those simulation codes scale out so well. And like we have supercomputers that run them, and like you can really easily run a lot of simulations about the Earth. But then you need a way to analyze those data that come out of it to actually get to some interesting science. And so I would say the core users of Pangeo are people who are analyzing very large ensembles of Earth system simulation data. That is probably like the core group. And from there, it's sort of diffused out to proximate areas like remote sensing analysis, analysis of satellite imagery and other measurements of the Earth from space, analysis of data that is collected from autonomous sensors and robots in the ocean or in the atmosphere, like weather balloons, things like that. Anytime someone is, I think, dealing with a data set that is too big to easily fit on their laptop or in memory on their computer, we think Pangeo can help accelerate those, specifically by actually using the same tools and the same code that you can use on small data for big data. Like that's the real beauty of Dask particularly, and like Pangeo gets that for free by using Dask, is that you can just have code that works on small data in memory, and then you can just have the same code working with a very large data set with distributed computing. And so the transition to scaling out your research is way less painful when you're doing it that way. In the past, what people were doing is essentially batch scripts on HPC systems, processing file, like a very file-centric workflow, like read this file, produce something with it, write out another file, like then do some kind of reduction or something like that. And the abstraction we're going for is that you don't have to think about files, you think about data sets, and you think about physical dimensions and coordinates, and that is the sort of code that you write it around, not what files do I have to process.
And I'll just add to answer the complete part of your question, which is what other scientific domains beyond climate and remote sensing and the geosciences. I think the life sciences is an area we're seeing parts of what we're working on in Pangeo get picked up. It's not a wholesale adoption, and it's actually one of maybe the best parts of Pangeo is that you can pick and choose the parts that fit your applications appropriately. But we're seeing applications in neuroscience, in genomics, and in bioimaging that are all using some different parts of what we would kind of consider the Pangeo ecosystem or the Pangeo stack.
Moving back to the file interface that you're trying to move away from, I'm curious in terms of the source formats that you're dealing with, how you're able to help people with managing that abstraction to say, we don't want you to think about the source files, we want you to think about the data set, but you actually still need to work with these source files to get them into the data set to begin with, and just some of that dimension of being able to work with all of these different scientific formats that can be quite esoteric and complicated, and sort of the multidimensional aspect of XArray comes in. But I know, like, for instance, HDF5 can be very complex in terms of what you stuff into it.
I think it's really important for us to shout out an organization called Unidata and a file format called NetCDF, a metadata convention called CF Conventions. Compared to other fields, I have learned that in geoscience, we're really lucky to have a great standardized file format that's really broadly used in our field and really good metadata conventions that come with that file format. So much work has already been done with geoscience data to make it, fair, findable, accessible, interoperable, reusable, right? Through the use of those kind of standards. The last mile that kind of we've had to cross with Pangeo is to just deal with the fact that like most data sets are distributed as many files, right? Like every now and then you'll find that like 100 gigabyte HDF file, but like for the most part, if you go download data from NASA, they're going to give you like one like 50 megabyte netcdf file per day. And there'll be like 10,000 of them for the data set that you want to work with. That's very common, access pattern. XArray does a great job with this. It has this magic function called open MF dataset, open multi-file dataset. And I think a lot of us, when we first started using XArray, this was just like the candy that made us love XArray. Just the fact that we could just instantly open this big collection of files and just treat them as one virtual data set. And it just is a huge cognitive load lifted off your brain to focus on the big picture. We started from a pretty good position. But of course, then once you try and scale out, you really come right up against like what are the actual I/O limitations of the computing hardware we're using, right? Like that's actually then where the bottleneck starts to lie. In a way, XArray can make things look too easy. It can instantly open and show you all these files. But then when you actually start trying to compute stuff, you have to deal with, well, how fast can my hard disk get me data? Or is this HPC file system, what kind of contention is going on here as I try to work with this? Or in the cloud, can I efficiently read this format? But it's good to be up against those limits. That means that you're reaching the saturation limit of what your computing hardware can deliver.
Something that's emerged out of this is some even higher level abstractions on large multi-file data sets. And so I think this is where kind of the catalog space comes in. And two projects we've leveraged quite a bit in the Pangeo ecosystem are Intake, which is a library for cataloging data and then loading it into Python objects, and then FSSpec, which is a library for accessing local and remote data under a common API. So I think these are two things that have really kind of changed the game for us and how we think about data organization and data access. And they plug in directly with XArray and Dask, and they work in the cloud, or they work on HPC, or they work remotely and locally.
Another interesting element of this overall problem space that you've touched on a couple of times is the advent of the cloud and its increasing popularity and the different access patterns that it enables and requires as compared to HPC, which is where a lot of this research and analysis has been done up till now. And I'm curious if you can talk to some of the challenges that this move to the cloud brings to this analytical flow and some of the ways that Pangeo is helping people make that migration off of these monolithic HPC systems that you have to try and allocate your timeshare onto versus the public cloud where you just need to give them a credit card and hope that your budget doesn't run out.
It's first important to say that our HPC centers that we have in science are an incredible resource, and the people who run them are really fantastic. We would be nowhere without them. So it's not HPC or cloud, it's really HPC and cloud. HPC has a really important role to play here. I don't think that's going to go away anytime soon. As far as cloud for us, like we got into it by accident, basically. We submitted this proposal in 2017, and NSF asked us to trim the budget. And one thing we put in that budget was, like $50,000 to buy a couple servers to like store data, because that's the kind of thing that, we put in proposal budgets. We wrote back to NSF, we said, okay, we'll cut these servers, but can you give us some cloud credits? Because at that time, NSF was running this program called Big Data. They partnered with Microsoft, Google, and Amazon to like just directly grant cloud computing credits to researchers. In retrospect, it was a very good marketing ploy by the cloud providers, because now we've become total cloud evangelists. So we got like $100,000 worth of Google Cloud credits, and we just kind of went nuts. In retrospect, it's remarkable how kind of fast and loose we played with this. We really just started spinning stuff up and trying things, but we basically stood up this cloud-based Jupyter hub connected to a bunch of cloud-based data, and basically let anyone who wanted to access it and play with it. And it was super fun and liberating to just be running and deploying our own infrastructure, right? If you're used to working with HPC, it's very much like a sysadmin versus user. Like you have to beg them to do things. Like they're very conservative, they're very security, aware. Resources are limited. They're large, but they're limited. And cloud, it was just kind of like a completely new paradigm. We could do anything we wanted. We could build anything we wanted. We had a lot of money, so we weren't really worried about like our spend. In retrospect, now all of those things become serious concerns as the project matures and we try to like actually run real production infrastructure. But at the time, it was very exciting and liberating. And we learned a ton of stuff. We experimented a lot. And I do think that we helped to chart a course into cloud computing for the geosciences and maybe science, maybe a little bit more broadly than just geosciences. Things are great in geosciences because we have very few restrictions around our data. We don't have, privacy. We don't have personally identifiable information. We don't have HIPAA regulations around, health data. It's basically all Creative Commons licenses, and you can just do whatever you want with it for the most part. And so we were able to just forklift data into the cloud and start computing on it, and it was awesome. One technical thing that's worth getting into is this whole question of cloud native data formats, right? So far we've talked about HDF and NetCDF. What we learned in 2017 is that we couldn't just put HDF data or NetCDF data into cloud object storage and compute on it in a convenient way because we didn't have a way to like open those files. They're really these complex, opaque binary formats, and there's like a C library that has to read them. At that time, it was just baked in that it's going to be like a POSIX file system where the data live. So you just had to like download the whole file if you wanted to even open it up. And so that didn't feel very like cloud native to us. What we really want is a data format that can just be accessed directly through HTTP calls, which is how object storage works, and where we can sort of get the metadata without downloading the whole file, and where we can efficiently subset or select from the data. So we experimented with a lot of different formats. Parquet is sort of the canonical example of a cloud-native format for tabular data. It's not ideally suited for multidimensional arrays. And so we really put a lot of time into working on XAR. XAR is an open source community-driven project that's more or less API compatible with HDF, but whereas HDF stores things in one single file, XAR just kind of explodes the data set into many individual metadata objects, which are just JSON files, and then binary blobs of data that can be compressed and chunked and stuff like that. And so we spent a lot of effort integrating XAR, Dask, and XArray to provide a real cloud-native workflow. And it's awesome. If you are working with XAR data in the cloud, using Dask to scale out on hundreds of compute nodes, you can absolutely burn through data, really just, getting right up against the limitations of the hardware, saturating the network, saturating the CPU, just really process data as fast as the computers will allow. That's quite exhilarating when you're doing that at scale. And it's part of, I think, the fun of Pangeo when users get to experience that.
It's interesting hearing about this because I have another podcast about data engineering, and it's very focused on what you're talking about with Parquet and these cloud native formats and scalable compute and analysis. And it's always interesting hearing the perspective from people who are dealing with more complex data sets and data structures beyond just the tabular. And so I'm curious if there's any sort of analog to what's happening in the data ecosystem with data warehouses and the quote unquote modern data stack and incremental stream processing, or, managing that whole data pipeline lifecycle as it applies to the geosciences and the just sort of general academic scientific exploration writ large.
It's a great problem because the modern data stack has so much momentum right now, and it really doesn't address scientific data, which means there's this huge opportunity as science moves into the cloud to build out that type of tooling, but focused on this more complex data model that we deal with in scientific research. And I think that's a super exciting opportunity. There's great patterns in the modern data stack, but the fact is I can't put, my climate model data in Snowflake, or if I can, they just call it, unstructured data. No, it's not unstructured. It's highly structured. It's just not the structure that those tools want to assume. What we are trying to build now with funding from the NSF EarthCube program is a framework called Pangeo Forge, which is an ETL tool focused on cloud native scientific data. You can think of it as maybe vaguely comparable to what something like Airbyte or Fivetran or Stitch does in terms of connecting data sources, ingesting data into a data lake, possibly with transformations in there, and storing it in a cloud native data catalog. That's where 100% of my sort of developer effort is focused right now. And we're really psyched about it. It's kind of just come alive. And I could probably talk about it for the next hour, but I'll leave it there for now.
That's great. I'll throw one more thing in here, which is that the reason Pangeo Forge needs to exist today is largely out of the success of the workflow and the model of using Pangeo tools in the cloud. We noticed a pattern, just like I was talking about earlier, how the kind of science workflow has found a bunch of detours that build general solutions to problems that we find over and over again. And as we've been developing the Pangeo cloud ecosystem, we found that one of the hardest and biggest pain points is getting data into cloud optimized and analysis ready data formats, and then pushing it and tracking it in the cloud. And so out of that need grew Pangeo Forge. And it's something that we feel like we could put a whole community effort into at this point, because it's the keys to the castle in terms of interactive big data geoscience going forward.
Spending a bit more time on the sort of cloud native storage format, I'm curious if and how much you've explored the TileDB platform for being able to handle these multidimensional data structures in this sort of matrix vectorized sort of storage format that is designed for the cloud, and maybe some of the limitations that it has that leads you away from maybe endorsing that in a full-throated manner.
We love TileDB. It's a great tool and a great format and a great company. I think the reason we haven't done more with it is a pretty simple practical problem, which is that XArray cannot write TileDB. XArray is our Swiss Army knife of data formats. It can read every format we know of, and it can write most formats we would want to write. And it has an extensible architecture through entry points that allow anyone, third parties, to implement readers and writers. For whatever reason, writing a TileDB writer for XArray has never been implemented. And therefore, we don't have the ability to create TileDB data. Almost all of our data is coming from a legacy data format. And so it's really just this one technical blocker. I think to some degree, there are some dynamics of the fact that there's a big company behind TileDB might make some people in the open source community a little less likely to just roll up their sleeves and do that work, kind of just hoping that all of that funding and all the engineers in TileDB, they can do that work. Whereas with Xar, there was no company. Now there's a few proposals that fund it, but it was more just everyone pitch in and let's hack this thing together and make it work. So that's really the only reason. I think TileDB, to be honest, is a technically superior format in most ways to Xar. It's very clever. It's very high performing. So in the future, I want to work with it more.
All right. Well, I consider that a challenge to the listeners.
Well, if someone wants to implement this, please do it. It would be a huge service to the community.
And so in terms of the overall sort of scope and the goals of the Pangeo project, I'm curious if you can talk to some of the ways that those have shifted from when you first began working on it to where you are today and where you're looking to go in the future.
In the early days, we had kind of three main goals: foster collaboration around open source Python for applications in the climate sciences and geosciences more broadly, support all these domain specific packages, and then improve the scalability of them to petabyte scale data analysis problems. Where we're at today is not that we've solved all those problems, but we've solved some of those problems. And what we're seeing as we've kind of transformed into something that's more there's probably more users in Pangeo than there are developers today. That's different than the early days, whereas most user developers or developers, is that Pangeo is kind of growing into more of an open science community. with a lot of people that are using the tools. And not to say that there's fewer developers, there's probably more developers, but the ratio is probably higher on the user side. When I say open science community, it's still a place where there's a lot of collaboration on how to use tools and on developing those software tools and also on data side. But the focus is kind of increasingly more on the science user than on the software packages themselves, which I think is a great evolution of a maturing project to see it move from, all right, here's like 3 software packages that we're developing on to here's a collection of tools and ideas and architectures that we can use to great effect on the problems, the research problems, the scientific problems that we're facing.
You said a key word, which was open science. And this is not something we talked about and used that word as much in 2017 as we do today. We can see huge momentum behind the open science movement from agencies like NASA, NSF. Open science is loosely defined as, open publications, open data, and open code, open source. But even something perhaps more that happens when you have that, which is a more collaborative approach to scientific research that I believe is very much inspired by what we have happening in open source. In the open source world, there's not really so much competition. I mean, there are some cases of competition, but in general, it's kind of this feeling that we're all in this together. Let's try and improve this software so we can all do better work. Let's work together. Let's not duplicate efforts. Let's try and find a place for new contributors. And I think a lot of scientists would like to be working with a similar ethical framework on their research. And so what I see for the future of Pangeo is to see if we can actually change the culture of science where we do our work more in the open and are more open to outside collaborators getting involved and augmenting our projects. And I think that's going to take science farther in the coming decades than the sort of more individualistic sort of siloed model has in the past. So that's an open question whether Pangeo can actually do this for the community. But I think we have become a concrete example of a real live, healthy open science community that others can look to for a model.
In terms of the work that you've seen both done under the auspices of Pangeo and maybe as a direct result of it, both technical and scientific, and in terms of the community, I'm curious if you can speak to some of the most interesting or innovative or unexpected ways that you've seen that come about.
A couple ideas that come to mind immediately is some of the operational uptake in Pangeo tools. So, Ryan mentioned NASA, but NASA and NOAA, two of the biggest public geoscience data providers in the world, adopted parts of the tooling and the approaches we've taken, in particular, as both of those organizations are moving towards using cloud as the place to store and distribute their data. We're seeing things like tooling being built using XArray or data being stored in XAR formats or cataloged using similar tools. And I think that's a really exciting thing. I mean, it's in many ways why, say, NASA or NSF are giving grants to organizations like ours is so that we can innovate these ideas to a place where they can be taken up by larger institutions. And so I think, NASA is certainly doing this, NOAA is as well, is a big success of the project so far.
Yeah, my answer is more or less the same as Joe's. I think it's been really cool and unexpected to see also organizations in Europe, like European Space Agency, building operational infrastructure, production level infrastructure for data processing out of these building blocks. I think in many times they don't explicitly credit Pangeo, and that's fine. They're like, this processing system is built, it's using XAR data, we're processing it with Dask, and we're providing, XArray, it's clearly Pangeo, but it's not credited, and that's fine actually and good. I think there's a world in which Pangeo becomes this invisible, layer, supporting these tools, and if they go out and are adopted and used and help the world, that's kind of best case scenario. The other direction is adoption in biogenomics and microscopy. That's super cool to see.
In your experience of helping to form and grow this community and the associated technologies, what are some of the most interesting or unexpected or challenging lessons that you've each learned in the process?
For me, it's been the management and fostering of a large distributed asynchronous community. It's taken a lot of energy. I mean, it's been incredibly fruitful, but there's also been a lot of coordination effort that has gone into that. When I started working on XArray, it wasn't to build a community. It was in part because there was a bit of community aspect to it. But as this kind of grew into the Pangeo project, it started attracting users and other developers. It became more and more a coordination project and less of a development project.
I echo that. Like trying to keep the community organized and moving forward and motivated has been a huge time sink for me. I mean, I think it's time well spent, but it really does take energy and effort. And I think sometimes we underestimated, like it's easy to start projects and start things, but sometimes we underestimate the cost of keeping them going. I think that's true in software and work more generally. I would add another challenge. It's good. It's always important to acknowledge, we really try to make our community really inclusive through code of conduct, through a lot of things we can do to try and welcome new users. But the fact is, the open source software development world is not the most diverse place. We've tried and had some examples of success to make our community more diverse and welcome contributors from more different walks of life and more different backgrounds, but we still have a lot of work to do there, as I think a lot of the scientific Python projects do. That's a perpetual challenge and something we're always trying to think about how to do better on.
And as you continue to work on and foster that community and the associated technologies, what are some of the things you have planned for the near to medium term future of Pangeo?
I think in the near term, Ryan talked about it earlier, but I think Pangeo Forge is a big effort right now. And I think that pushing on this data lake concept for geoscientific data in the cloud is a big aspect there. There's other areas of growth within the Pangeo project that are not necessarily connected to Ryan and I, but I think it's worth saying. I think there's this early stage shift towards more of an open science community, and there's others pushing on that. I think that's really exciting. I also see there's a group at the National Center for Atmospheric Research and at the University of Washington that have recently got support to do software support across the ecosystem, which is something that it's really quite easy to get grants traditionally to build new things. But NASA has a program now for supporting open source software, which is both really cool and there's going to be focus in the Pangeo space on that. So there's a whole mix of things. The community is really multidimensional in its own way now.
I really think cloud can be transformative for science. I think a lot of people get wrapped up in the technical or the cost, analysis and miss the broader point that cloud allows us to be way more collaborative internationally, around research. And I think that will have really big impacts on science. And I think, it doesn't mean we have to use Amazon cloud, but cloud broadly defined as this open internet environment for doing science, I really do think is going to transform the way we work for the better. As far as Pangeo goes, I'm very interested in building bridges with other languages, particularly R and Julia. As far as simulation goes, I'm very bullish on Julia in the future. I think in 10 years, a lot of our work is probably going to be in Julia. Pangeo has there's interoperability today between Pangeo and Julia. The ZAR format, for example, has really good Julia support. You can call Python from Julia and Julia from Python. But I think just continuing to build out that bridge is really important for sort of looking to the future, because I see a lot of great innovations happening in that community. I've dabbled in the language myself, and I think that's going to accelerate.
Are there any other aspects of the Pangeo project and your work in that community and the technology stack that we didn't discuss yet that you'd like to cover before we close out the show?
It's a good time to highlight the fact that there's a discourse forum. Pangeo is fundamentally an online community. It's not based at any one institution. It's on GitHub, and we have a discourse forum. And so that's discourse.pangeo.io, on GitHub at Pangeo Data. I think those are the nexus of collaboration, and encourage folks that are interested to go check those out. There's also a weekly meeting that is about half the time. It's a showcase where people can check out presentations or demonstrations on things that people are doing in the space.
I think it's also really important to shout out, like a lot of people ask, like, how can I learn to use Pangeo, which you might just translate as how can I learn to use like scientific Python and these various packages. But there's a great group that's focused on the education side within Pangeo, which is called Project Pythia. This is a collaboration between some folks at NCAR and the University of Albany. And they have a great website, a really rich Jupyter book with awesome sort of training material. It's really a 0 to 60 course in scientific Python computing in the geosciences. So if anyone is hearing this and wants to know where can I start, that's a great place to start.
All right. Well, for anybody who wants to get in touch with either of you and follow along with the work that you're doing, I'll have you each add your preferred contact information to the show notes. And so with that, I'll move us into the picks. And with spring coming, and once I get on the other side of mud season, I'm excited to get back out and do some mountain biking. So for folks who haven't given that a shot, definitely a fun way to spend your time. So with that, I'll pass it to you, Ryan. Do you have any picks this week?
A way more indoor pick, but I just read the novel Clara and the Sun by Kazuo Ishiguro. Really blew my mind. It's about AI. It's about artificial friends and the potential where we might end up if we really manage to create very, very advanced AI and put it into human-like bodies. It was very thought-provoking and a beautiful book, so highly recommended.
All right. And how about you, Joe?
I'll have to see you out on the trails on the mountain bike. Also looking forward to that. But last year I finished a book called Range by David Epstein, and it's about how generalists thrive in a specialized world. And I thought it was a really interesting take on why, a bunch of experiences and a more generalist approach is important in the world we live in today.
All right. Well, definitely going to have to take a look at both of those. So thank you for taking the time today to join me and share the work that you're each doing on Pangeo and helping to give more people access and capacity for doing analysis and data science on large geospatial data sets. Appreciate all of the time and energy that you and the rest of the community have put into that. And I hope you each enjoy the rest of your day.
Yeah, it was a pleasure. Thanks for having us.
This was awesome. Thanks, Tobias.
Thank you for listening. Don't forget to check out our other show, the Data Engineering Podcast, at dataengineeringpodcast.com for the latest on modern data management. And visit the site at pythonpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts@podcastinit.com with your story. To help other people find the show, please leave a review on iTunes and tell your friends and coworkers.